We learned in topic 4 that whenever you apply a non-zero net force, the object will have a change in motion or change in velocity called an acceleration. Well, now we're going to discuss the equivalent for rotational motion, which we're going to refer to as torque. So in order to have a change in angular motion or an angular acceleration, a non-zero net torque needs to be applied to the object. In some ways, torque is going to be easier to calculate than forces, and in other ways it's going to be slightly more complicated. So we're going to get into the details of that throughout topic 8. So the first thing I'm going to do is explain how we're going to calculate torque. Torque, represented by the Greek letter tau, is going to equal our lever arm distance times the force applied. So R is going to be the distance from where R equals 0 to where the force is applied. And when an object is actually rotating due to the force applied, we're going to set R equals 0 at the rotation point. And we already know what force is, but we do have to be careful here. Only the force perpendicular to R is going to cause a torque. So let's explore this a little bit further and look at a door. So imagine this is the hinge and you're looking down at the top of the door so that the doorknob is sort of sticking out here. And I like to use a door example because we use doors every day and we open them and close them. So we apply a force even though we don't realize we're doing it because we're applying a force to the doorknob, which then pushes on the door. Now if I apply force 1 here and I apply force 2 here and I say that force 1 is equal to force 2, let's talk about what happens to the torque. Because even though the forces are the same, the torque is not going to be the same. So we have R1 here and R2 here. So R1 is less than R2. And remember, torque is the distance from the 0 point. So our 0 point is here at the hinge to where that force is applied. So because the force is the same and the R's are different, that's going to change what the torque is. So torque 1 is going to be less than torque 2. And this is something we know. This is why doorknobs tend to be on the point furthest from where the hinges are rather than close to the hinges. If you ever encountered one of those doors that have the metal bars that you're supposed to push in order to open, you probably had an experience where it's hard to tell which end is the one with the hinges, so you push on the end near the hinges and the door doesn't open, you push on the other end, then the door does open and you feel a little silly. So we have encountered that in everyday life, where we know the torque is greatest at the point furthest from the rotation point. Now imagine we have force 3 here. So this would mean, and normally and when I do this in class, I would open the door and actually push sort of where the lock is. And whenever you're pushing there, the door doesn't move. You need to apply a force perpendicular to the door, not parallel to the door, and actually to get it to move. So because the force is parallel to R, no torque is applied. Now what happens if we apply a torque at an angle, or not, well, a torque or a force at an angle? So let's say we have force 4 here, and we have an angle theta in here. That means I need to pull out my components again. So we would have force for X and force for Y. Now remember, the force has to be perpendicular to R in order to cause a torque. So in this case, we would need to use the Y component. And since the Y component is opposite to the angle provided, I would say in this case that the torque is equal to the force times R times the sine of the angle provided. Now let's talk about whether torque is negative or positive. So we'll say torque is positive when it causes counterclockwise rotation, and torque is negative when it causes clockwise rotation. So this goes along with the idea of lefty-loosey, righty-tighty. So if you turn the screw to the right, it goes in because you're tightening the screw, and if you turn the screw to the left, it pulls out or you're loosening the screw. So you've actually been applying physics whenever you've been saying that phrase to remember how to loosen or tighten a screw or a bolt. So all the arrows I've drawn so far in this diagram would cause a counterclockwise rotation and be positive. It isn't until I draw a force in this direction, because my rotation point is right here. So you have to imagine the door is fixed at the rotation point, and so the force is moving here would cause the door to rotate clockwise, and thus would be a negative torque. Torque is a vector, but luckily, because the force has to be perpendicular to the lever arm to cause a torque, we're only worried about negative and positive torques. We don't have to worry about X or Y components like we did for force. But in order to find the net torque, you do have to find each individual torque caused by each individual force and then add them together. And that's what you're going to practice by doing the example problem on page 1 of your lecture notes.